Welcome my dear students. How are you? Today we start a very important topic in laws of thermodynamics. So today we state about two important topics in first law of thermodynamics. That is, today we discuss about internal energy of a system and indicator diagram. These two topics is very necessary to understand first law of thermodynamics. Now, what is internal energy of a system? Internal energy is the sum of kinetic energy, and potential energy of a system in a reference frame with respect to the system which is at rest in its center of mass. This is the definition of internal energy. The sum of kinetic energy and potential energy of a system in a reference frame with respect to the system which is at rest in its center of mass. Or simply, the sum of kinetic energy and potential energy is known as internal energy. Suppose a system is a gas is placed in a container. So, the molecule of a gas have intermolecular attraction. Now, if we give heat from outside, then the gas wants to extend, that is increase in its volume. So, work is done by the gas. As a result, the intermolecular potential energy, intermolecular potential energy also increase. So, when a gas expands or takes expansion, then its intermolecular potential energy is also increased. So, intermolecular potential energy is a function of, if we take it V, is a function of volume. As volume increases due to expansion of gas, the intermolecular potential energy increases. So, the internal energy also increases. Next, internal energy in forms of kinetic energy. In every gas, the molecules are in random direction, moves in random direction, random motion or direction. This motion may be three types. One is translational, one is rotational, and one is vibrational. Now, when we give heat from outside, again the translational, rotational or vibrational motion increases, which increase its kinetic energy. Therefore, kinetic energy is a function of, that is kinetic energy E is a function of temperature. Kinetic energy E is a function of, kinetic energy E is a function of temperature. So, internal energy depends on volume and temperature. Because the potential energy and kinetic energy is together known as internal energy. When a gas expands, its volume increases, so its intermolecular potential energy increases, and also when heat is given from outside, that is work is done by the system, so the increase in kinetic energy, that is one of the translational, rotational or vibrational motion of gas, so its internal energy increases. But for an ideal gas, the intermolecular force is 0. As we know from kinetic gas theory, the intermolecular attraction force for an ideal gas is 0. So, for ideal gas, internal energy is only a function of kinetic energy, that is it depends only on temperature. For ideal gas, internal energy is purely a function of temperature only. I hope you know the concept of internal energy. Now we go with heat, difference between heat and work. What is heat and what is work? Heat is a mode of transfer of energy. Work is also a mode of transfer of energy. But transfer of energy, that is heat, is depends on temperature difference. But work does not depends on temperature dependence or temperature difference. Heat is due to temperature difference, heat flow from hotter to cold body, but work is does not depend on temperature difference. 3. Heat is random in motion. Energy transformation in random motion is called heat, because when heat is supplied, the molecule goes in random direction, in every possible direction, no in a particular direction. But in work, it is mode of transfer of energy in an organized way. If we put some gas in a container and give heat from outside, it expands. If we put some weight on it from the outside, then and press it, then all the molecules will goes in the direction of force of piston. Then all the molecule goes in direction of force by piston. So, the molecule does not goes in any random direction. So, the work is an organized way of transfer of energy, but heat is random motion of energy. This is very important of first law of thermodynamics. Next, we go with the PV indicator diagram. Any thermodynamic system can be defined by any of two variables. Any thermodynamic system is defined by any two variables, because when the two variables are known, the third variables is adjusted in so arranged way. That is, if two variables are known, the third variable is automatically solved or known. We know that for a thermodynamic system is expressed by such variables volume, temperature, pressure, density rho and mole of substances. Now mainly these three are V, T and P are thermodynamic variables to define completely a thermodynamic system. If we take volume V along x axis and take pressure P along y axis and a graph is drawn like this manner along rectangular hyperbola graph, then it is known as PV indicator diagram. Suppose this point is A where the graph is initiated and B, and if the gas expands then its direction from A to B. The coordinate of A is P1 V1 and the coordinate of B is P2 V2. Draw two perpendicular from this is C and this is D, or put this D and this C. Then this is perfect way of expansion of gas. Expansion of gas. Now the area, this area, that is area enclosed by the PV indicator diagram and the volume axis, this is volume axis. The area enclosed by PV indicator diagram and the volume axis is equal to work done. This is total work done by the gas. Total work done gas by equal to area of PV diagram. That is area enclosed by PV indicator diagram and the volume axis. Here ABCD, here area of ABCD. Now if the gas is compressed in spite of instead of expansion, then the diagram will be same, but here A point is P1 V1, but the B point goes up P2 V2 and the direction is reversed in this case. Here this is C and this is D. What is the difference between the two graphs? This is gas compression, compression of gas. Here work done is positive, here work done is negative. Here work done W is equal to positive, here work done equal to negative. And the area is taken here is clockwise direction, that is A, B, C, D. But here the area is taken as anti-clockwise direction A, B, C, D. So the direction is reversed from this. And this is work done by gas, this is work done on gas. Work done by the gas is always taken positive, work done on the gas is always taken as negative. This is true for any cyclic or non-cyclic relation. Next lecture we go with cyclic and non-cyclic work done. So here some sign convention is required. We take the sign convention, that is if heat is absorbed then it is positive, if heat is flows out from a system obviously it is negative. Heat is absorbed by system, it is positive, that is the value of H is positive, and if heat is flows out from the system it is negative. Number 2, work done by gas is always taken as positive and work done on gas is always taken as negative. Work done by gas is taken as positive, work done on gas is taken as negative. Number 3, work done in clockwise positive and work done in anti-clockwise, negative. Work done in clockwise direction, it is positive, and work done in anti-clockwise direction, it is negative. This is the sign convention for first law of thermodynamics. So, today lecture we can know the internal energy, which is the function of volume and temperature, and for ideal gas it is only the function of temperature, and also the PV indicator diagram and work done whether it is positive or negative. Next day we go with cyclic and non-cyclic process and the work done by the cyclic process or non-cyclic process. If you like my video, please subscribe, comment and share it. Thank you.